I would like first to thank the organizer for the invitation. So I'm happy to be here. So I am a professor at Rennes University, and I have an INRIA team there on cryptography. So most of we are doing cryptanalysis, and since 3 years, in fact, we hire some researcher in quantum algorithm. And that's the reason why I begin to work on this area, but I am mostly a beginner in this area, and I would like to present you some of algorithms that are useful in cryptography, and also we work a little bit on this algorithm. Okay. I would like to first to introduce you a little on cryptanalysis. Then, in particular, maybe you will see that we are interested in the number of gates or the implementation of quantum algorithm in order to evaluate the security of the primitive. And so we will mainly go into the detail of the circuit to understand exactly how it works. So the work are maybe a little bit more in the implementation on quantum circuits. Okay, so after an introduction on cryptography and cryptanalysis, I will briefly speak about some quantum circuits for Dutch-Rosa and Simon's algorithm. So Simon's, in fact, is the algorithm which has been developed just before Shor algorithm. And I think it's good to start with this algorithm because it has some implication in cryptanalysis, and also it is maybe easier to understand than Shor algorithm at first. Then I will describe Shor algorithm, and at the end, maybe not for this lecture, but this afternoon, I will go into a very recent quantum factorization algorithm that have been developed to show you that there is a lot of things that we can do in order to improve Shor algorithm. Okay? Cryptography, in fact, is a science of secrets, and it means that we want to achieve confidentiality, integrity, and authentication. So confidentiality, I think everyone knows. So when you send a message on internet, you want that only you and the intended person is able to read the data. And for this, in fact, we use encryption scheme. And there is also two other kind of security notion, integrity and authentication. And integrity means that when you send a message to someone, you want to detect if there is a bad guy that try to change the message. And authentication, when you receive some data, you want to be sure that it's the correct person that sends you the information. Okay? So this is, in fact, the three goals that security can achieve. And for this, in fact, we use either encryption scheme to ensure confidentiality or signature scheme to ensure integrity and authentication. Okay? So there is also some other work to ensure using symmetric key cryptography, integrity, and authentication, but I will not go into this detail now. So in fact, there is two kinds of cryptography. So the first one is secret key cryptography. So it's something that is very old, since in fact about the beginning of the writing. So it's so maybe you heard of Caesar code. So it's very old, and but quite recently, 50 years ago, in fact, some researchers found public key cryptography. So the difference between secret key and public key is that for secret key, so both persons, so the sender and the receiver, share the same secret key, while for public key, in fact, everyone knows my public key, for instance, and in this case, everyone can send me a message. Okay, so basically you can think that it's like my phone number. You can use my phone number, and I am the only people that are able to call with you. Okay, so this is a public key cryptography, And in fact, for public key cryptography, we developed a lot of mathematical tools. Okay, so now we have a cryptanalysis. So cryptography is the good guy. So the people are trying to design secure scheme, and cryptanalysis are the bad guys that try to break, in fact, what the cryptographer developing. Okay, and cryptanalysis, an adversary in cryptography is just an algorithm, and so it can be either classical or quantum. And in fact, we need, to evaluate the security of the scheme. And to do this, in fact, we have to compute exactly the complexity of our algorithm or circuit to evaluate the concrete security of our scheme. Okay? So a public key cryptography is a little bit different from secret key because, in fact, we cannot ensure perfect secrecy. So perfect secrecy has been developed by Claude Shannon. Yesterday, you see that one-time pad is one of the schemes that can ensure perfect secrecy. However, for public key, you are forced, in fact, to use some computational assumption. So computational assumption is something that we don't know how to prove that it's very hard, but we assume that it's hard to break some mathematical problem. Okay? And last, I would like also to speak about security level. So if to break your scheme, you need 2 to the 128 step, in fact, we will see that the adversary is not able to do so many steps. Okay, so we assume that your crypto system, if you need 2 to the 128 operation, is safe against some adversary. So the other is that the logarithm of this number of steps is what is called the security level. Okay, so 128 security level is good, while 64 is bad. Okay, so you see that, so this is just a factor 2 on the exponent, but in fact we need to clearly understand the security. Okay, so why 64 is bad is because in fact, we can do 2 to the 64 operation, maybe not on a single computer, but if you have a cluster computer, it's doable to do this computation, while 2 to the 128 operation is quite costly, and you don't think about beginning such a computation. Okay, so the first, maybe we will go into the detail for public key cryptography. So the first scheme is the RSA schemes that have been developed at the end on the 70s by Rivers, Shamir, and Adelman. And I will not explain you how RSA works, but you just have to remember that if you are able to break, to factor the RSA modulus, then you will be able to recover the secret key. Okay? So the factorization problem is this problem. You have n, which is a product of 2 very large prime numbers. This is called RSA modulus. And so the goal is to recover one of the 2 non-trivial factors. Okay, so one non-trivial factor is, it's not plus or minus 1, neither plus or minus n. Okay, we want to retrieve P or Q. So maybe just to illustrate how such algorithm work, try to factor 8051. Do you know how to factor this number? No. So there is a trick, in fact. Sorry? Yeah, well, first solution is that, no, you can't. You can't divide by 3, but one idea is to start to divide by all the prime number to the square root, and you will find one of them. Okay, so you begin dividing by 3. So dividing by 3 is 8 plus 5 plus 1. Sorry for the interruption. So maybe you have time to try to factor this, or maybe to find the trick to factor this number. Sorry? Yeah. But let me just, yeah, you're right. Let me just maybe try to factor this number. Maybe no one found the trick. So maybe it's easier. So 91, yeah?
The difference between two squares?
Between two?
The difference between two squares?
Yeah, exactly. So in fact, 91, you can write this as 100 minus 9. And so now it becomes easy to factor a square minus b square. And and it is exactly the same here, but the decomposition for 8051 is 8100 and minus 49. Okay? So yes, one of the factors is 83. Yeah. And in fact, all of the factorization algorithms basically are related to this idea. Okay, so we are trying to decompose the numbers that we want to factor into the difference of two squares, and if we are able to do this, we will be able to factor with some probability. Okay, so the most efficient classical algorithm is NFS. That is, in fact, an improvement over the quadratic sieve algorithm developed by Pomerance during the 80s. And in fact, so the complexity is a little bit hard to understand, but it's 2 to the cube square of n, when little n, in fact, is the length of the modulus. Okay, so in cryptography in particular, we are interested in small, little n of 100 to 2000. Okay? So this complexity is called super polynomial or sub-exponential. So it's between, in fact, a polynomial complexity. You see that it's 2 to the something, and below 2 to the n. Okay? So the complexity is not 2 to the 2000 something. It's very, very something that is doable, in fact. And for instance, some record shows that. So you see that for this number of bits, so it's about 250 digit number. So it's quite large, but some people have been able to factor such number with a huge computational power. Okay? But it's something that is doable today.
And just to have an idea of this algorithm, does it also use the trick of?
Yeah, exactly. But in fact, it works in two different related. You have to use, in fact, number fields in some way, and the rational in the other way, and you found some decomposition like this. Okay. But yeah, it is exactly the same kind of ID, basically. Okay, and for 2048-bit modulus, so we expect that the complexity is 2 to the 128. Okay, so you see that when we are doing cryptanalysis, in fact, we want to know, we are not just interested in the complexity of the algorithm, but also in the constant in the complexity. Okay, and the constant in the complexity here matters a lot to understand the security concretely. Okay, because we want that this number to achieve, and if it is 2 to the 64, so it will be broken. Okay, so we really need to understand the complexity of our implementation. Okay, so the second problem is what is called the discrete log problem, and in fact is not completely related to factorization, but not too far. And so in this case, we are working in the ZP star. So this is a field because P is a prime number. And in fact, so we can see that this group, in fact, is cyclic. So we have a generator for this group. Let me, so it's something. And also we have some group inside this cyclic group. And in fact, we are interested in a prime order subgroup. Okay, so G is a prime order subgroup of ZP star. And in fact, we have some element in the subgroup, and we want, in fact, to recover the value X. Okay, so the value X, if you forget the mod P here, in fact, you see that you want to recover X from G to the X, so you compute a logarithm of Y in base G. And in fact, we called it a discrete logarithm because it's mod P. Okay? So let me just show you all of this number with some example in order to understand more clearly how it works. So we are working in P with P equal 11 and G equal to 2. Okay, so now I can in fact compute all the power of G mod P. And you will see, so the first one is 2 to the 0, so it will be 1, 2 to the 1, so it will be 2, etc., etc. And at some point, we reach 2 to the 4. And 2 to the 4, in fact, is 16, but mod 11, it will be 5. Okay, so when we are working modulo 11, just think that 11 is equal to 0. Okay? And in this case, every time we have a multiple of 11, it will be 0. And so basically, we just remind, in fact, the remainder of some value divided by 11. And so the remainder of this division is between 0 and 10. Okay, so if we continue, we have 2 to the 5. And to compute 2 to the 5, the idea is not to think 2 to the 5 is 32. And you want to compute the division of 32 by 11. So the idea is that you can just use a 5 here. And 2 to the 5, in fact, is 2 times 2 to the 4. And so 2 to the 5 is also equal to 5 multiplied by 2. So it will be 10. Okay? It will be 10 here. Okay, and we continue up to some value. At some point, we are back to 1. Okay, so maybe some of you know why we are back to 1 at this point for 2 to the 10. No, it's a well-known theorem in arithmetic. So it's called Little Fermat theorem that says that if P is a prime number, something that is not divisible by P, if you raise it to the power P minus 1, so you go back to 1. Okay? So this is a famous theorem of Fermat, and it explains why we are back to 1 at this point. Okay? So here you can see that we have all the number except 0, and in fact in ZP star, so we have all the number except 0. Okay? So let me just draw some picture of this. So we can arrange all of these values around some cycle. And we begin by 1, which is 2 to the 0. And here we have 2, 4, 8, 5. Here I put 10. Here I have 9, 7, 3, 6, and back to here. So I think I have all of this value. So now I can be interested in some subgroup. Okay, so subgroup here is that maybe what is a group generated by the element 4. Okay, so the group generated by 4, we begin also in 1, and we go from this to this, and we take, oh, maybe I missed some value here. I don't know which one. 9, 7, 3. Yeah, sorry. No, I have 8 here, sorry. Sorry, here, 2 by 2. Okay, so the subgroup generated by 4 contains exactly all of these 5 values. Okay? And there is another subgroup also which is generated by 10. Okay, so if I use this value, I can go there, and now from this, I go there. Okay, yeah?
I didn't get what is the route to link to...
I said, so the first thing I do is, what is the subgroup generated by 2? Okay, so now I write what is the subgroup generated by 4. Okay, so the subgroup generated by 4 is this one. I have 1, 4, 5, 9, 3, and I'm back to 1. Okay, if I'm interested in the subgroup generated by 10, I have 1 and 10, and I go there. Okay, so maybe it's not easy for you, but what is the reason for the subgroup generated by 10 is contain only 2 elements? Because if you compute modulo 11, so 10 is equal to -1. Okay, you have different way to represent integer mod 11. Either you use a representation between 0 and 10, or you use some representation between -5 and 5. Okay, so this is possible, and this number is equal to -1. And so the reason why, when I have a -1 to the power 0, so it will be 1. -1 to the power 1, it will be -1. And now, -1 to the square, it will go back to 1. Okay, so here you can see that I have, in fact, and you can see that we have this subgroup, so it's ZP star. The subgroup here generated contain only 5 elements. And the subgroup generated by 10 contain only 2 elements. Okay, so it's not a surprise here, because in fact there is a theorem that says that when you have a cyclic group, and if you are looking for, which are here p-1 element, so all divisor of p-1, there is a subgroup that has exactly this number of elements. Okay, so here we have 10, and the divisor of 10 is 1. So what is the subgroup generated with only 1 element? So it's only 1. Okay, so if I care here. The subgroup generated to have 2 elements, so it's a subgroup generated by 10. With 5 elements, so it's a subgroup generated by 4. And the subgroup generated by 2 has exactly 10 elements. Okay, so for all divisor of p-1, you have a subgroup. Okay? So this is a general case, and so for the discrete log, I can take any divisor Q of a prime divisor of p-1, and I will be sure that there will be a subgroup of this kind of order. Okay, so it's not also difficult to generate this value. It's just, so we can do this randomly very efficiently. Okay, so that means that the best algorithm to break discrete log is that there is some clever way described by Polar that you square root of Q. Okay, so if you took Q too small, there will be some attack. And also, if P is too small, there is an attack, so it's a variant of NFS. Okay, so the same algorithm that for factorization can be also adapted to discrete log. It's not the same algorithm, but it's not too far. Okay? And so the prime P that we use usually is 2048-bit number, and Q is 256. Okay, so this is basically the numbers that you want to have in order to continue further. Okay, so in 1994, when Shor described his quantum algorithm that is able to do this in polynomial time, so it was really a shock. because he was able to factor, in fact, in polynomial time, and so the complexity is a little bit more than this, but asymptotically we can expect to do this. So it's n square, in fact, the size of the circuit, and the number of qubits will be, in fact, it will be 3n in the best implementation, okay? So if we are able to construct, in fact, such quantum computer, so we will be able to break all the communication. Okay, so that explains why, in fact, since 2015, the NSA began to think that we need, in fact, to change all the algorithm, because a lot of people are, at that time was, in fact, speculated about computing, and a lot of new results in physics shows that maybe it could be possible at some point. And so cryptographers have proposed what is called post-quantum cryptography. So post-quantum cryptography is, in fact, to replace RSA and discrete log scheme using some other kind of mathematical art problem, okay? And for this problem, we conjecture that there is no quantum algorithm to break them in polynomial time. Okay, so it's only conjecture. As for RSA and factorization, we have some conjectures that it's hard to break factorization using a classical computer, and at some point it's true, okay? For this, so the assumption is a little bit stronger. We hope that there is no classical algorithm to break them, but also no quantum algorithm. Okay? So that's why, in fact, cryptographers now have to look at the security of this new mathematical problem using quantum algorithm. Okay? So it's really a new field that is interesting to work in. Okay? And so the problems are of different nature. So this is based on different kind of problems which are related to lattices, Euclidean lattices, and coding problem. Okay, so there are other kind of variants, but it's the two main applications today. And now the standard, some of the standards are available since 2024, and so the transition in fact begins. In fact, all of the communication today, if you use Chrome or some other browser, in fact, some of them use post-quantum cryptography. On Signal, on WhatsApp, also a lot of applications have moved to this new kind of cryptography. Okay? Do you have any questions so far? No. Okay, so now let's go to some basic algorithm in order to understand how they work. So first of all, something that is interesting for our algorithm is what is a partial measurement. In fact, we will have, and at some point Thomas explains this, but let me just remind you a little. So for instance, you have a 2-qubit state, so it can be described using 4 complex number, and maybe you will observe the first qubit, and it will be 0 or 1, and if you observe a 0, what does it mean for the second qubit? Okay, so it's, for instance, you have a ket psi here, and you see that this is a superposition of only these 3 qubits. And so if you see, if you observe the first qubit, if it is a 1, what can you expect for the second qubit? Sorry? 1, okay, thank you. Yeah, you can expect that this is a 1, yeah, exactly, with probability 1, okay? But what is if you observe 0? How it will change, in fact, the second qubit? Okay, so to understand how it changes it, in fact, you try, in fact, to factor the value there. In fact, here you can factor with the first qubit 0, and you will observe the new qubit. Okay, so here I factor with this value, so I have this new superposition. So this is the second term, I don't care about this. And here, so this is in fact the second qubit, and I can normalize it in order to find the value. Okay, so this is something that is very general. If you have any qubit, a 2-qubit state, if I observe 0 for the first qubit, the second qubit will be changed like this, and I just have to normalize this qubit, and it's exactly what I did. Okay, I can do also the same if I observe 1, so now I have to normalize this qubit for the second one. Okay, and in fact, in Shor algorithm, we will use this. We will, at some point, observe part of the state, and it will change, in fact, the other part of the state. Okay? Okay, so here there is just another example. You can also do this using 3 qubits, and it's just some exercise. And if you measure 0, 0, so you can have a different state for the third qubit. Okay, so you just have to factor here by 0, 0. So you have these two different kind of value, and now it will be 0 and 1 accordingly with some probability. Okay? So now the second thing is what Yacine told you. So it's Oracle, and usually in cryptography we have some function, but the function is not always reversible, and in order to create a quantum circuit, we need to modify and change the circuit in order to be reversible. Okay, so the idea is something that is very useful in cryptography. It's called Festel scheme. And Festel scheme is in fact a way to transform a random function into a random permutation. It is something that we want to have here. Okay, so just let's assume that we have only the group z over 2z with addition. So here it just means that the addition mode 2. Okay, so the addition mode 2 is very easy. You have 0 plus 0 equals 0. 1 plus 1 equals 2, but 2 equals 0. 1 plus 0 is equal to 0 plus 1 is equal to 1. Okay, so this is very simple. And now I have a function, and this function goes from some set E and this value to this value. Okay, so first I have this function, and I want to make this reversible. And so I will construct this oracle that will be reversible. And now the answer is that if I have x, I have the identity here, and for the second component, I will have x, y XOR f of x. Okay, and this will be a bijection or permutation. Okay, so it's not difficult to prove that it is the case. So I can, in fact, compute the inverse of this function, and in fact, it's an involution. So to see this, I just apply f twice on this value. So f, capital F of x and y, it will be x and y XOR f of x. And now, if I apply it twice, so I will have x for the first input, and for the second input, I will have y XOR f of x XOR f of x. And since I am working mode 2, in fact, I have 2 times f of x, and 2 times f of x is equal to 0. So I have y XOR 0, and y XOR 0 is y. Okay? Okay, you understand? So it's just a way to work with that. So it's something, for cryptographer, it's easy because we like working with XOR operation or modulo 2, but maybe when you see this, it's not completely easy. Okay? So we know how to transform, in fact, any function in some oracle. However, you see that you need to pay some price. In fact, the input of the function is much larger than the output. Okay, so here the output are just 1 bit. Here the output, we need all the qubits in order to make it reversible. Okay? So for the first example is, so we will use what is a Dutch-Jozsa problem or algorithm. And the idea is the following. You have some function, f, from 1 bit to 1 bit. Okay? And so you have, in fact, 4 different kinds of functions. Okay? So the first function is the function f0. So it sends 0 and 1 to 0. Okay, and the second is that send 0 and 1 to 1. Okay, so you see that these two functions is what I call constant. Okay, so output is always the same value, is always 0 or 1. Okay, here for the value f2 and f3, you see that here the output can be different. I have 0 and 1, and here I have 1 and 0. Okay, so the function f2 and f3 are what I call balance. So balance is when you have as many 0 as 1. Okay? And in fact, a function with 1 qubit to 1 qubit is always either a constant or balanced. Okay, so it's always the case, and because I have only these 4 functions. Okay, so classically, how many queries you need to ask to F in order to solve this problem? So the problem is you have a function in some black box, so you don't know which of these 4 different functions is, and you want to decide if it is either F0 or F1, so if it is a constant function, or if it is a balanced function. Okay, so classically, so the idea is just in fact, you need to query F0 and F1, and you compare, and you decide afterwards. Okay? And in fact, quantumly, you can do this only with 1 query to the black box. Okay, so in fact, you may think that it's not an exponential factor, yeah, I agree with you, but in fact, now if I generalize this problem, I take as input an n-bit function, and with 1 bit output, okay, and now, in fact, all the functions are not in these 2 categories, either constant or balanced. Okay, there are other functions that have not an equal number of 0 and 1. For instance, you can have 2 0 and 8 1. Okay, it's possible. Consequently, it's not a constant. It's neither a constant nor a balanced function. Okay. So in this case, I promise you that the function is either constant or balanced. Okay, and I ask you to decide which case it is. Okay, so classically, in fact, you can show that it is exactly, you have to query the black box, in fact, 2 to the n-1 plus 1 query. And in fact, you see that it is exactly the same value here with n equal to 1 here. Okay, but in fact, quantumly, you also need exactly 1 query. Okay, so this is a much impressive result. Okay, you go from something exponential classically to something constant here. Okay, so how works the circuit? So the circuit is more or less always the same for all the algorithms that we will see. Okay, so the algorithm at some point is preparing some superposition here. Okay, and here we will do some, at some point we will ask the oracle. Afterwards, we will only here apply some Adama transform for the first part of the circuit, and then we will see what is the output. Okay, and our oracle is exactly the function here I described you before. Okay, so the circuit is the following. So the state here is very easy. So psi1 kept psi1. So I just apply the Adama state here for the first qubit, and so it will be this. Okay, so I remove all the 1 over square 2 factor in order to make this a little bit more readable. And so here I don't touch the second qubit, and now I will move to this value. And so the Adama state, when it is a 1 as input, will be this output. And so now I just have to develop everything, and you think that you have a kind of superposition of all states. But in fact, here, for the first qubit, you have exactly a superposition of the 2 qubits here. Okay? So now I will go through the oracle function. And so here, I just remind you the state here. And so I will go through this oracle. Okay, so in fact, according to what is the first qubit, I will do, so the first qubit will be always the same, and here it will also be in the output of the second qubit. Okay? So you can see this. If I begin with the 0 qubit here, the second qubit will be, so this 0 is in fact the value y here, and here I have f of x. Okay, so here I will have y, and the second qubit will be f of x, and I can do also the same for these two qubits. Okay, and now I can in fact try to factor in fact this qubit into something that is smaller, and here you can see that if f0 is 0, so I have 0, I have this value, and if f0 is 1, so I have this value here. Okay, so the value a can be a factor into this value. Okay, and I can do in fact exactly the same for the value here, and so in some way I can in fact write more compactly in fact the formula for this the state here. Okay, and now I go to the last part. So we have to apply the Hadamard gate here, and so if I apply the Hadamard gate, I can apply here, so it's not too difficult. And now I come up with this state here, which is a superposition of all these qubits. Okay, and now what will be the output here? Okay, so to understand what is the output, in fact, you need to factor in some way the output qubit. So you have 0, 0 here, you have 0, 1, 1, 0, and 1, 1. Okay, and now we play this value, so the game. So if f is constant, so if f0 is equal to f1, and if it is equal to 0, so it's not difficult to see that this will be equal to 2. Okay, and if it is 1, so it will be equal to -2. Okay, the same also appear here because you have exactly the same value. While here, in fact, you have alternate the sign here, and so according to if the function is constant, so you can have either you have all of these two different qubits, but you don't have this value. Okay, all these value cancel, and you have only these two different states. Okay, so basically, if you at some point you observe 0, so the first qubit, if you observe the first qubit and if it is 0, it means that the function is constant. And if it is equal to, and if the function here is balanced, so it will be this case, all of this value will cancel, and at some point the state will be this. Okay, so just by looking at the first output, if it is 0, you just answer that the function is constant. If it is balanced, so if it is the first bit of output is 1, you just have to say that the function is balanced. Okay, so in fact you just have to apply the function f once here. Okay, however you do this in superposition, it's why you gain something exponentially. Okay, so I will not explain you how it works completely, but if you want, so something that is a good exercise is to try to do exactly the same, but now with a 2-qubit function. Okay, so your function now have 2 qubits as input, so the circuit will be this. Okay, 2-qubit input and 1 output, and now you will have to check in fact the first 2 qubits here, and if it is 0, 0, it will be something. Okay, so here you will see we have some Hadamard that will compute here a superposition of all the state. You apply the function, and here we apply Hadamard before the observation. Okay? So now I will move to Simon's algorithm. So Simon's algorithm is also a very nice problem, I think. And it's very also helpful in cryptanalysis, and just after the presentation I will show you some application. So the function now, we have n-bit input and n-bit output, and you have the promise that the function is 2 to 1. Okay, so each output can be only achieved using 1 or 2 inputs. Okay, and you have also something very special, is that you have some constancy that is magic, you don't know which one it is, and you know that f of x is equal to f of x XOR c. Okay? So for instance, you can have this function from 3-bit to 3-bit. Okay? Here you can see that you have 1, 0, 1, so you have different value. Here you have a different value. Here is still different from the first one. Here also, at some point here, you will be back to this one. Okay? Here also, it's exactly the value here. Okay, so it's exactly what is the functions that we are interested in for Simon's algorithm. Okay, and the goal is in fact to recover what is the magic C constant. Okay, so here you can just see that you have some collision between this value and this value. Okay, and in fact you can see that if you have collision here, that means that the difference between these two inputs is by C. Okay, so in fact you can see that 0, 0, 0 is in fact 0, 0, 0 XOR the constant. Okay, so if it is the case, so we have x is 0, 0, 0, and also XOR C is equal to, 1, 1, 0. And in fact, to compute C is not difficult, so you just have to do the XOR or the division, so it will be x XOR x XOR C, and here it's equal, so the XOR is just 1, 1, 0 here, and now it's 2 times x, so 2 is equal to 0, so you can remove this. Now it will be 0 XOR C, and 0 XOR C is equal to C, and so the output is this. Okay? So it's very easy to play with the XOR. Okay? So if you have two values that map to the same output, so it's very easy to recover the magic constant. Okay? So how works the algorithm? So they compute, in fact, the function f up to some collision, and once a collision appears, so it's very easy to deduce, in fact, the magic constant. Okay? There is another solution. Maybe you can see that these two values, these two values here are different. And so if the two values here are different, it means that the constant cannot be the XOR between these two values. Okay, so you can deduce that C is in fact different from this value. Okay, since here also you see that this value is different from this one and this one, you also deduce that the magic constant is different from the XOR of this value and this value, and this value and this value and this value and this value. Okay, but it's something that is not very useful to with inequality, but sometimes it's possible, and we can see that the number of calls to the function is exponential. Okay? Okay, so how can we solve this problem quantumly? So just here is a reminder for the Hadamard transformation. So Hadamard transformation is the simple way to see, in fact, fast Fourier transform. So here, the root of unity is just plus or minus 1, so it's very easy. And in fact, the algorithm works as follows. So we have, in fact, two n-bit inputs. So here we have the first register with n-bit input, and here the second register with n-bit input. Okay? So I will go through, in fact, for the first register, so on each of the n first qubit, I will apply the Hadamard transformation. So I just apply the Hadamard n time, and at some point I will get a superposition of all the state. Okay, so here x is in fact equal to all the bit string using n bit. Okay, so I have all the integer between 0 and 2 to the n minus 1. Okay, and now I will apply the function f. Okay, so the function f, exactly, it will use this value x, and it will apply this, and it will be 0 XOR f of x. Okay, so it's exactly how works the oracle f. And so what we will see is that at some point we will measure the second qubit. Okay, so in this superposition here, so in fact you can see that this superposition can be written more precisely. And in fact, for each So in fact, you just have to look at the value here, okay? And for each, and this value, so you will have many different values. So for instance, you can in fact do this with a small example that I showed you before. And here you will have different value with only one output and many also with two output. Okay? And the value with two output, in fact, will have a higher probability than the value with only one output. Okay? And for instance, for these two different values here, I have 0, 0, 0, and at some point I have 1, 0, 1. And I have also the value here, 1, 1, 0, 1, 0, 1. And yeah, maybe. So this will be, in fact, here I have the first 3 qubits, and here I have the second 3 qubits. Okay, and you see that we have here, I can factor with the output here, and here at input I have this superposition. Okay, and I have this also for the second collision. Okay, for the second collision, in fact, it will be on 0, 1, 0, and here the output is in fact 0, 0, 1 plus 1, 1, 1. Okay? While for the other output, for instance, for the output 1, 0, 0, I have only the value, the x is corresponding to this value. Okay, so here I have the value f of x, while here I have the value x. Okay, you understand? So I can in fact factor according to the second qubit because I am observing the second qubit. Okay, and once I observe the second qubit, maybe it will be this value, and the output of the first qubit will be this superposition. Okay, and we can have a higher probability to observe this outcome for the second qubit than this one. Okay, because here we have the addition of two different values. Yeah.
Why is there only 1, 0, 1? The value 0, 1, 1 also.
Is this one? Yeah. I agree with you. I have also this here. Yeah. I agree. Yeah, it could be this. Yeah, sorry. So I haven't looked at carefully. Yeah. So all the values appear twice here. 1, 1, 0, 0, 1, 1, 2 times. Yeah, every value appears 2 times. Yeah, sorry. Okay, you're right. Okay, so I have, at some point, if I observe this state for the second qubit, so I know that the first qubit will be this superposition. Okay? So now sorry, here I measure the second qubit, and here I just wrote you what is in fact the content, the state of the first n qubit. Okay? So here, if I observe some value, so I can deduce that the first qubit is the superposition. Okay? And now I have to deduce what is the magic constant. Okay, but I can't in fact do this using one observation. If I observe in fact this, I will have either this state or this qubit. Okay, but I will not have both. And I need both in fact to deduce what is the constant S. Okay? However, what is in fact the impact of the Hadamard transform on this state? So if I apply the Hadamard here, so here I just apply here using the formula using x0 here because it's linear, and here I factor with the value y, and here I rearrange a little bit the different term. I factor with this value, and I can have this value here. Okay? So, and in fact, in this superposition, so it's not too complicated to see that in this superposition, you have either 0 or 1. So here, the value y here, this value will be either 0 or something different from 0. Okay? So if you have here something different from 0, that means that here the value is different from 0. And if it is different from 0, that means that x, in fact, is orthogonal with y. Okay? So here I just remind you that this is a scalar product. S is n-bit value, y is n-bit value, and I compute the scalar product on z over 2z. Okay? So at some point, I got, so I will have the value y when I observe the output, and I know that S, in fact, is orthogonal to y. Okay? But I've not been able, in fact, to recover S. Okay, so what can I do? In fact, I will repeat this algorithm n-1 or n time, and at some point, if I got some value y that are independent of them, then I will have a linear system that is very easy to solve. Okay? And if I solve the linear system, so I will have one vector in the kernel, and the vector in the kernel will be exactly the value S that I'm looking for. Okay? Do you understand how it works? So the first thing is that I begin with 0, 0. I apply a Hadamard transform. I apply the oracle once. I observe the second, I measure the second register, and then this is the output of the first register. I apply the Hadamard transform on the first register, and when I measure, I will have one value, one vector that is orthogonal to S. Okay? When I have one vector that is orthogonal to S, I repeat this procedure n-1 time, and then I will deduce the value S. Okay? Yeah?
I'm not sure I understood how to go from measuring second register to apply H. Like, how do you get this formula?
Which one? That one or that one?
The first
Here? Yeah. Here, in fact, this is, when I measure the register, I will have here some value. So,
I got how you get x0 plus x0 plus S.
Okay.
But I don't get the action of the Hadamard.
So, in fact, I will apply this Hadamard from the rule state. Okay, and Hadamard is linear, so I will apply the Hadamard from this value. So I will have this here with this formula. Okay, so I replace J here with x0. So I just do this. And I do also the same for x plus S. And here I have x0 plus S. Okay? You understand now? Yeah, so it's just this formula that I applies twice with x0 and s0 size. Okay. So I agree that here I just in fact factor with the same y here. Okay, but I agree that here I have also the sum over all the value and y. Okay, and here is just in fact some I factor with this value because it appears here and here, and so here I have some different value. Okay, so you see that once I measure, in fact, the second register, in fact, the first register collapses completely on one of these different rows. Okay, and so maybe I observe this, and so the first register will be these two values. So it's what is important. Okay, so how it can be used in cryptanalysis? So it's so there is a lot of people that try to apply this for doing cryptanalysis on symmetric work. So it works like this. So it's let me explain you a little bit on symmetric cryptanalysis, cryptography, for instance. So in fact, we want to construct block cipher. So block cipher basically is a n-bit to n-bit function, and that use, in fact, some key material. So here, for instance, I have n-bit input, okay, that will be mapped to some n-bit output. So this is usually called the plaintext, and this is called the ciphertext. Okay, and you can ask, in fact, to the encryption box many different value x, and you will receive the corresponding ciphertext. Okay, and the goal of the adversary is, given so many plaintext ciphertext pair, to recover the key material. Okay, so the key material is another input of the algorithm. Here I have two n-bit keys, okay, and I apply here some function that is a public permutation. Okay, so in this scheme, everyone knows exactly how functions the function p. However, all the secret is in K1 and K2. Okay, and in fact, it's hard to compute K1 and K2 given some plaintext ciphertext pair and also given access to the public permutation here. Okay, so if I write, in fact, the computation of this block cipher, in fact, it can be written like this. Okay, I first apply the key K1, I apply the permutation, and after I apply the key K2 just using XOR. Okay, so you have access to many data with plaintext and ciphertext, and the goal is how could you deduce the value K1 and K2. You also have access to the public permutation here. Okay? So our goal is to recover the secret key. And in fact, classically, it can be shown that if, since you have access to the public permutation, you can do this completely offline. And so just you need time to compute as many plaintext input and output of the P function. And you can, in fact, try to record a lot of input-output of the function P. Okay? And the second thing that you can do is also to query the block cipher. Okay? Because if you just query P, so there is no key that is involved in this computation, and so you will not have information about the key. Okay? So now you will have some information about the key if you use the block cipher. Okay, and if you use the block cipher, it's what is called the data. Okay, so the data is a lot of different plaintext ciphertext pairs that you collect using interaction with the block cipher. Okay, and it can be shown that in fact, in order to recover the key, you need that the time, so the number of queries that you made to the permutation P times the number of data that you have has to be in fact n to the power n. Okay, so that means that you can spend, in fact, a lot of time with interaction with the permutation P, and maybe deduce the data accordingly, but the product of these two is equal to this. Okay, no matter how you can do this. Okay? So this is one of the nice results. And you can see that what you can do is, if you want to have an efficient scheme, is that if you take t equal 2 to the n over 2, and d also 2 to the n over 2, so here you will see that you have 2 to the n over 2 complexity. Okay? If the data is too costly, maybe you can reduce the data to 2 to the n over 3, but in this case, that means that you need to spend more time with interaction with the function P. Okay? So, but to me, in fact, you can do something very smart. In fact, you can use Simon's algorithm. And so the first thing you can do is that you can transform, in fact, this, the block cipher here into some periodic function. Okay, so the idea is just, you just XOR the output of the block cipher and the output of the P function. Okay, so here you can see that the block cipher is equal to P XOR X XOR K1, XOR K2, and here I have P of X. Okay, so this is the function that I'm interested in, and you can see that if I compute x XOR k1. So here I will have XOR k1 XOR k1, so it will be x. And here I will have x XOR k1. And since addition is commutative, so P of x XOR P of x XOR k1 is equal to P of x XOR k1 XOR P of x. So I will have this value at some point. So you can see that in fact our function is exactly like this. And so in fact, with just, so in fact we need an oracle to implement the function here. Okay? And we just need one query to this computation in superposition. Okay? So this is in fact a little bit strange for cryptanalyst, because for cryptanalyst, maybe all of these values that you collect, you use in fact a classical computer, but you don't have a quantum implementation of your algorithm using some secret key. Maybe at some point when we will have a quantum computer, it will be interested in having block cipher using some keys. Okay, and then we will have implementation of block cipher, quantum implementation of block cipher. Nowadays is not possible, but at some point it could be possible. And so nowadays it is not a realistic model. Okay, because the block cipher is running classically. We don't know the key, but here in fact to do the Simon's algorithm, we need to have an implementation of the block cipher with the same keys that is running on quantum computer. Okay, so I don't think that is very useful in practice, but it's a case. Okay, so here you can see that in fact, oh sorry. So yes, it's not, here there is some typo, it's not one query to this in superposition because I explain you, I need n-1 query to run Simon's algorithm. Okay, so it's just n-1 query to the block cipher in superposition, and I will be able to deduce the first K1, and once K1 is recovered, so it's not a big deal to recover K2. Okay, because once K1 is recovered, in fact, since P is public, you can compute all of this value, and just with one plain text and ciphertext pair, you recover K2 by just XORing the result. Okay, so the recovery of K2 is very easy. Okay? So I don't know if you have to stop here, or maybe, so I don't know if I begin a little, or it's up to you for show algorithm.
En fait, on va te donner une demi-heure. Tu auras commencé une demi-heure en avance
cet après-midi.
Et donc, so the idea is that we start early.
I think it's possible. Here it's possible.
So I think we will take question. So to allow Pierre-Alain to finish talking. Yes. So we will stop now and take question for Pierre-Alain and what we will do is this afternoon we will start early. Well, we can discuss how much time you need, but we have a longer break this afternoon, so this will allow to adjust. So we will start early for Pierre-Alain, and maybe it's good to stop here and to take question. So we have
I have very naive questions about the rule at the beginning of the talk. The product of the two prime numbers, which is the difference of two square. Is it only when it is the product of two prime numbers you have always this?
You can always, all time you can do this, in fact. Okay. There is a lot of decomposition.
I'm not sure that why did you say that it's not realistic? I'm not.
Yeah.
Kind of, maybe a bit fast.
Yeah, it's because in fact So here, now, so the implementation of the block cipher is on classical computer. And so you have some classical computers that allows you to compute something, but you don't know the key. Okay? In order to implement Simon's algorithm, I need, in fact, to implement this function quantumly, okay, on some circuit. And so I also need a quantum implementation of the block cipher with the same key that I am trying to attack. So nowadays, so I have only a classical implementation of block cipher, but at some point, maybe if we will have a quantum computer, it will be also interested in to program block cipher on such computer, and in this case, it will be possible to have some quantum implementation of the block cipher. Okay.
The hard part of the presentation.
So,
Can you repeat?
Yes.
Sorry, I don't understand.
I just asked what is the complicated part to implement in a quantum computer?
Is that because in fact, so it's a key here, because we don't know the key in fact, and we can't in fact implement it. So I agree with you that it's just a circuit, and normally it's possible to do this, but here we need, so we don't know the key, and so we don't know exactly the implementation. Okay, yeah, good question.
If I understand correctly, the algorithm finding the period S uses some promise that the function is 2 to 1 or something like that. But here,
Yeah.
Are we sure that
Yeah.
satisfied?
Yeah, exactly. It's so this is so do you agree with this relation?
Yeah, the fact that there is K1
Yeah.
is a period, but there we have something else.
Yeah, maybe you're right, you have to take care because those are in fact two different permutations, and the output is in fact a random function. But yeah, it's not completely easy to do this, to check this.
Another question for Piranha? If not, well, it's time to go to break.
Thank you. So Shor algorithm is just, in fact, Simon's a little bit more complicated than Simon's algorithm, but it's closely related. And in fact, at some point, you will see exactly the same kind of circuit. And the big deal is just to implement correctly the oracle function. Thank you.